A gyroscope is a spinning wheel or disc in which the axis of rotation is free to assume any orientation. When rotating, the orientation of this axis is unaffected by tilting or rotation of the mounting according to the conservation of angular momentum. In layman's terms, a gyroscope is a spinning disc, rotating, and then mounted such that it can freely rotate within the structure, or the structure can rotate around the gyroscope, such as when used in an aircraft, as we will see later. The following is taken from the most recent edition of the Federal Aviation Administration's publication, The Pilot's Handbook of Aeronautical Knowledge, Chapter 7, page 15. There are two fundamental properties of gyroscopic action: rigidity, in space, and precession. Rigidity in space means the gyroscope remains fixed in the plane in which it is spinning. Thus, if the gimbal rings are tilted, twisted, or otherwise moved, the gyro remains in the original plane. Rigid, in space. Let's watch a few gyros in action. Up first is a video produced by the United States Navy in 1960, used to train pilots on the mechanics of their flight instruments.
To understand any gyroscopic instrument, you must understand the principle of the gyroscope. It consists of a rotor, mounted in a gimbal. The rotor can spin in one plane only. When another gimbal is added, a second plane of movement is possible. And when this assembly is mounted in bearings, the rotor has three planes of movement and can assume any possible attitude. This is now a freely mounted gyroscope. A spinning gyro has two important properties: precession and rigidity in space. All of its practical applications are based on these two properties. As for rigidity in space, the spinning rotor remains in its original attitude, while the gimbals and base move around it. In other words, the gyro maintains its axis in relation to space and not to the surface of the Earth. If a gyro moves around the Earth, its axis is vertical to the Earth's surface here, at an angle here, and horizontal here.
The spinning wheel prefers to stay oriented as it is, and it resists any attempt to change that orientation. The fact that gyroscopes will maintain a particular orientation in space is very useful. In modern aircraft, an inertial guidance system uses spinning gyroscopes to monitor and control the orientation of the aircraft. The gyroscope is suspended in a special cage that allows it to maintain its orientation independent of the aircraft's position.
An attitude indicator, also known as an artificial horizon, is an instrument used in an aircraft to inform the pilot of the orientation of the aircraft relative to Earth's horizon. It indicates pitch, fore and aft tilt, bank, side-to-side tilt, and is a primary instrument for flight in instrument meteorological conditions. Pilots must rely on this instrument in order to maintain control of the aircraft during flight in IMC.
Each instrument continuously indicates the roll and pitch attitude of the aircraft in relation to the actual horizon, and each obtains this information from a freely mounted gyro. The axis of the rotor is vertical and, due to the property of rigidity, will remain in this position as the aircraft assumes any attitude. Therefore, the gyro establishes a vertical reference from which roll and pitch deviations of the aircraft can be measured.
Another excerpt from the Pilot Handbook states, The gyro is mounted in a horizontal plane, and depends upon rigidity and space for its operation. The aircraft actually rotates around the spinning gyro. Now that we have a fundamental understanding of how the gyroscope and attitude indicator works, let's contemplate an intriguing and quite contradictory scenario. A scenario that occurs every single day during every single flight. When an aircraft takes off, climbs to its final altitude and levels off, the attitude indicator depicts a perfectly level attitude. As the aircraft travels towards its destination, sometimes in excess of 7,000 to 8,000 miles, the aircraft's attitude indicator maintains a perfectly level attitude. This, as we have seen, cannot be correct, because the gyro maintains its original position in space, regardless of the aircraft's attitude, or its position on the Earth. According to known gyroscopic properties, a pilot flying by reference to his attitude indicator should in reality begin to fly away from the Earth, as the gyro will continually give a straight line from the plane in which the aircraft started. Again, it is stated that the attitude indicator is reliable and the most realistic flight instrument. It gives an instantaneous indication of even the smallest changes in attitude, and, since the gyro relies on rigidity and space, the aircraft actually rotates around the spinning gyro. Therefore, we can logically only conclude two answers to our problem. Either A, the gyroscope operates on a set of properties unknown to modern physics, in which case, many aircraft must be susceptible to potential errors from an instrument we truly do not understand. Or B, our world is not what we have been told. The curvature of the Earth is not what is claimed by NASA, nor is it curved much at all, lest the gyroscope would read inaccurately during every flight. One can only conclude that the gyroscopic properties are fundamentally true, and therefore the world in which we live has a few more questions that need answering.
If you just give it a little push, it just sits there and tumbles end over end. It's not a very stable platform. Now we're going to turn it on and watch what happens. And it's got a CD in there and it's going to spin up. So while it's spinning up, it starts to rotate the opposite direction. Then once it reaches steady state motion, it just sits there. And now look, when you push on it, it's spin stabilized from a gyroscope inside out of the compact disc. It's amazing that a spinning CD provides enough stability to show this kind of behavior.
For additional proof of the attitude indicator and gyroscope issues, let's take a quick look at the math as given by NASA for our globe model. The standardized formula to calculate the curvature of the Earth is given at 8 inches per mile squared. That means, you take the distance in miles times itself, and then times 8 inches. This formula is quite accurate within a few thousand miles. Additionally, an aircraft traveling 6,000 miles at an altitude of 40,000 feet would have to consistently drop over 450 feet every minute, and would have a total downward pitch change of 43 degrees, just to stay at the same altitude. This would be quite noticeable from the cockpit, and would cause many more issues with air travel, if it were true. But we know it's not. Aircraft do not have to deal with the rotation of the Earth. They do not have to deal with the curve. Why not? Answers from NASA are vague and lacking, and the modern scientists who promote the current model of Earth will not begin to look into these issues. much less present repeatable and verifiable evidence for the ball model. Question your world. You just might learn something. For more information on this topic and others similar to this, please check the links in the description for this video.